Chapter 5. Sequence as a whole. Section 1. Set operations. Now, we have learned to use a sequence, but this sequence looks like what we said before. It is a batch of variables with the same name. When we operate on these sequence members, we still refer to and assign values one by one. In this chapter, we learn how to operate a sequence as a whole. Sequence is essentially a set, though it is easy to think that it can support set-related operations, that is, intersection, union, etc. SPL provides for set operators. One is vertical bar, A1 vertical bar. B1 means to append the members of sequence B1 to sequence A1 to form a new sequence and return, which is called concatenation. The other three operators, ampersand, caret and backslash, are the set union, intersection and difference operations of common significance respectively. We used to represent the integer division operation with backslash. Here we use it on the sequence to represent the difference set. It is important to note that, unlike the mathematical disordered set, the sequence is ordered, which will lead to the difference between A1 ampersand B1 and B1 ampersand A1, and that the sequence intersection and union operations in SPL do not meet the exchange law. The ordered set also allows duplicate members. When performing intersection, union, and difference operations, it will be more complex than the set without duplicate members. Please carefully observe the above operation results to understand the operation rules in this case. In addition, SPL also supports the operation between a sequence and a single value, which is equivalent to the operation with a one-member sequence. The single value can be placed to the left or right of the operator. We use the set operation to rewrite the Narcissus number program. Concatenate the calculated Narcissus number to the current sequence with vertical bar operator. Pascal triangle. Use inner loop to calculate the middle part of the current row, and then concatenate one before and after it respectively, and then concatenate it as a whole to the end of the target two-layer sequence. As a kind of data, sequence can also be compared. The results of these judgments are all true. The conventional dictionary sorting method is used in sequence comparison. Each pair of members is compared in order, and the values of the first pair of unequal members is used to draw the comparison result of the sequences. If it is always equal, the longer sequence is considered larger. If all the corresponding members are equal and the length is the same, the two sequences are considered equal. In particular, because of order, the sequences composed of same members are not necessarily equal. We used sequence 0 times n to generate an all-zero sequence of length n. SPL also provides the to function to generate a sequence of integers. The result of column A is equal to the sequence of constants in column B. SPL refers to the sequence whose members are all integers as an integer sequence. Regarding the loop statements we have learned, we can find that for n, for AB are basically equivalent to for to n and for to AB. Here we say basically equivalent rather than equivalent, because the loop variable values of the former two at the end of the loop are different from those of the latter two. The sequence numbers of the sequence members are also integers. We can get the members from a sequence to form another sequence according to the sequence number specified by the members of an integer sequence. For sequence A, an integer sequence P, in SPL, AP can be used to represent AP1, AP2 until APK, where k is the length of P. AP is called the generated sequence of A. B1 will get the 5th, 2nd and 6th members of A1 to form a sequence, that is, 5, 8, 4. For the sequence composed of some continuous members in a sequence, it can be obtained by the to function of the sequence. A2, A3 and A4 can be simplified into B2, B3, B4. Note the writing methods of B2 and B4. The comma in B4 cannot be omitted. A5 and B5 are interesting calculations. Please observe the results of them by yourself. Usually, the generated sequence is part of the original sequence, which can be called a subsequence at this time, but an integer sequence may also have duplicate members, so the generated sequence is not always the subsequence of the original sequence. Section 2. Loop functions. Previously, we used the loop statements to complete the sum and max or mean operations for the sequence members, but the loop statements are very troublesome and we need to set the initial value first and then calculate step by step. SPL takes this into account and provides some common functions for sequences. It's easy to see the meaning from the names of these functions, and then execute this code to observe the operation results to confirm. The count function is a bit like len function, but count does not count members whose values are null. The average is defined as sum divided by count, not count divided by len. We will popularly call the functions that calculate the sequence into a single value aggregate functions, which are equivalent to aggregating the set. These aggregate functions all use the object syntax of x.f. In fact, SPL also supports writing these functions in traditional form, while sequence members are used as parameters. We've used the max-mean function before. It should be pointed out that len function is not regarded as an aggregate function. It actually gets an attribute of the sequence and does not actually traverse the sequence members to calculate the result. Therefore, the len function does not have this way to write the sequence members as parameters. We know that using toN function can generate a sequence, 1, 2, until n, and then using sum function can get the sum, so we can easily calculate the sum from 1 to 100 with two 100.sum, which is much simpler than the previous code of loop statements. So, what about the sum of the first 100 odd numbers? Do we have to write loop statements? No, SPL has thought about this and provides a way to generate a new sequence of the same length from an existing sequence. This expression 2 times 2 minus 1.sum can calculate the sum of the first 100 odd numbers. We can understand the left 2 and the right sum, but what is the times 2 minus 1 in the middle? For the sequence a.x denotes a sequence of the same length formed by calculating the expression x for each member of A in the same order. In expression x, the symbol tilde is used to represent the member of A which is participating in the calculation. The sequence 1 2 3 times 2 minus 1 is the sequence 1 times 2 minus 1, 2 times 2 minus 1, 3 times 2 minus 1, that is, 1 3 5. Just replace tilde with each sequence member in turn, and tilde is actually the loop variable when the sequence loops. In this way we can understand 2 times 2 minus 1.sum. Similarly, 20 times sum can calculate the sum of squares of 10 numbers from 11 to 20. A.x.sum is a common writing method. In SPL, it can be simplified to A.sumx, which is simple and easy to understand. Furthermore, the functions onto n are also commonly used, and SPL allows them to be simplified as n.f. Adding consecutive integers from 1 to 100 can be written as 100.sum. And the first 100 odd sum can also be written as 100.sum times 2 minus 1. Isn't it very simple? The functions that calculate on each member of the sequence and get a new result after traversing all the members are generally called loop functions. A.x, aggregate functions, and simplified form of A.f are all loop functions. Euler found a formula related to pi like this. We use it to calculate pi in reverse with just one expression. The accuracy of the first 1000 items is enough. There are many formulas related to pi, here is another one. With the help of if function, it is easy to implement. The syntax of loop function is very concise and efficient. Let's simplify the example used in learning loop, and calculate e. When we used loop statements before, we used an intermediate variable to calculate the factorial of n, but it seems that it can't be written in tilde, is it right? Actually, we can also use an intermediate variable in an expression. The code without loop statements is rewritten like this. The expression in sum uses the comma operator, that is, a, b, c until x will calculate a, b, c until x in turn, and the final result is x. The nf times equals tilde, 1 over nf in parentheses will calculate nf times equals tilde, then calculate 1 over nf, and the final result is 1 over nf. Comma operator is also invented by C language and inherited by SPL. It can be used to write a small number of multi-step operations in an expression to avoid writing multiple statements. The expression of the comma operator usually needs to be written in parentheses to ensure that it will not be misidentified. For example, if the outer parentheses are not written here, it may be considered by the sum function to be multiple parameters to perform sum, which leads to the wrong result. Now that we've learned the usage of the comma operator, we can also use it to combine two pieces of code into one. For Fibonacci sequence, we can calculate the first n terms of the sequence since we have the weapon of sequence. A2 will calculate the first 20 terms of Fibonacci sequence. The expression here does not use tilde, which acts as a loop variable. The loop function is only used to realize repeated calculation. This code seems a little difficult to understand. Its principle is the same as the example code when we talked about loop statements before. We will not elaborate on it anymore. Please think for yourself, draw the process on the paper and execute it by yourself. Section 3. Advanced loop functions. SPL provides tilde symbol as loop variable in loop functions, which can simplify a lot of code originally written with loop statements. But we know that the loop statement for sequence also provides the syntax to obtain the loop number, that is, add hash before the loop variable. So, is there something similar in the loop function? Yes, simply use the hash symbol. A2 calculates the difference between the sum of odd and even members of sequence A1. Using hash, we can calculate the sequence by contraposition addition of members of two sequences with the same length. A2 will calculate A1 1 plus B1 1 until A1 5 plus B1 5. Sequence A stores the sales of a company from January to December in turn. Now we want to know the maximum monthly growth, that is, the maximum difference between a member and the previous member. This can be realized with hash. When hash is greater than 1, that is, not January, we can calculate the growth of this month compared with last month. The last month value can be obtained by A1 hash minus 1, and the growth amount can be obtained by subtracting the last month value from the current month value tilde, and finally we just need to calculate the maximum difference. In the calculation of loop function, it is very common to refer to an adjacent member. SPL provides a special symbol, tilde followed by -1 in square brackets to represent A1 hash -1. The code can be simplified as -I in square brackets denotes the ICE member before the current member, and I in square brackets denotes the ICE member after the current member, that is, A1 hash plus I. Different from using AI to get a sequence member, when using square brackets, the calculated sequence out of sequence range will not report an error, but will get a null value. Let's try an example of referring to a member after the current member. Calculate the average sales value of each month and the months before and after it, that is, in the nth month, calculate the average sales value of the n-1th month, the nth month and the n+1th month, which is called moving average. We only calculate a 2-month average for January and December. Note that we can't simply add up and divide by 3, but use the average function, which will correctly handle the situation with null values. We can also simplify the calculation of Pascal triangle by means of the writing method of tilde square brackets. Here we make use of the convention that tilde -1 in square brackets will get null when it is out of bounds. In addition, the writing method of tilde square brackets can get a continuous subsequence. For example, for the previous data, we want to use the monthly sales sequence to calculate the monthly accumulated sales. The code can be written like this. Tilde to 0 in square brackets means from the sequence head to the current member, which is equivalent to A1.to hash. The complete writing of this syntax is tilde A to B in square brackets, which gets A1.to hash plus A, hash plus B. If A is omitted, members will be retrieved from the beginning, namely A1.to hash plus B. If B is omitted, members will be retrieved till the end, namely A1.to hash plus A. The method of getting a subsequence can also be used for the previous example of getting the moving average. Similar to loop statements, loop functions may be nested in multiple layers. For example, we calculate the sum of the products of each two members in two sequences. It's not hard to write with loop statements. But if we write with a loop function, there will be an obstacle. This writing is obviously wrong. The innermost tilde times tilde will calculate 1 square. We originally wanted to multiply the tilde of outer A1 by the tilde of inner B1, but now there is only one tilde symbol and we can't distinguish it. This problem can be solved by introducing an intermediate temporary variable. In addition, SPL also stipulates that adding a variable name before tilde can represent specified tilde, while tilde without a variable name will represent the innermost layer tilde, which makes it easy to write. A1 dot tilde denotes tilde of outer layer A1, and another tilde without leading variable denotes tilde of inner layer B1. If the outer loop function is for a sequence without a variable name, it can't be referenced. In this case, we need to use a variable to assign values in advance and give it a name artificially. To calculate the sum of all multiplication terms in the 9 multiplication table, we need to give to 9 a name in order to distinguish the layers in the multilayer loop function. While it is impossible to distinguish the inner and outer layers by writing 9.sum directly, because 9.tilde is not a legal formula. Sometimes the inner and outer layers are the same sequence, even if it is copied to a different variable, they still cannot be distinguished. The writing of B1 has the same result as writing sometimes directly, and it is impossible to distinguish the inner and outer layers. The writing of B2 seems to be able to distinguish, but A1 and A2 are actually the same object. You can review the content of the previous chapter. In the calculation of loop function, tilde is recorded in this sequence, and the inner and outer layers can still not be distinguished by only using different variable names. To write like B3, copy A1 to a new sequence, tilde of A3 and tilde of A1 will be different, and the correct result can be executed. It's the same rule for hash, and you can try to understand what these examples are calculating. SPL also has a function a.runx, which is similar to a.x. This function also calculates x in turn, but still returns a, not the sequence of x. What's the use of this? X can be an arbitrary expression. We said that equals is also a suitable operator. When using a.runx, we can use tilde equals to change itself. For example, a.run tilde equals tilde times tilde will change a into a sequence of the square of its members, which is different from a.tilde times tilde. The latter will return a new sequence, while the former modifies the original sequence. Doesn't this seem to make any difference? Yes, the new generation of sequence is no different from the modification of the original sequence for subsequent calculations, and when only tilde is used for calculation, there is no big difference. But if we refer to adjacent members with the help of the square bracket symbol, the result will be different. For example, a.run tilde equals tilde minus 1 plus tilde will change a into a sequence of cumulative values. While a.tilde minus 1 plus tilde is different, it does not calculate the cumulative value, but only the sum of adjacent values. Because a new sequence will be generated in the latter, and tilde minus 1 and tilde are all of the original sequence a, which will not be changed in the calculation process. However, the former does not produce a new sequence in the calculation process, and tilde minus 1 will be changed by the last round of calculation, resulting in the effect of cumulative value. The results of a.run tilde equals tilde minus 1 plus tilde and a equals a.0.sum are the same, and both of them can calculate the cumulative values, but the former needs much less calculation, because it is calculated on the basis of the previous round, while the latter needs to calculate from the beginning every time. You can try it with code. With this mechanism, we can simplify the calculation of e, abandon the use of a temporary variable, and use only one expression. In this code, the 20.run tilde equals tilde times if hash is larger than 1, tilde minus 1, 1, will get the sequence of factorial values, that is, factorial value of 1, factorial value of 2, until factorial value of 20. Before each cycle, tilde minus 1 is already the factorial value of the previous round, and then times tilde is the factorial value of the current round. For the first round of loop, we need to process with if, because SPL specifies that any number multiplied by null results in null, which is different from addition and requires special handling. With the sequence of factorial values, it is easy to get the result with another step of doing sum. The power of loop functions is huge, and you can write very simple and elegant code if you use them properly. Section 4. Iterative function. We can also use more basic iterative function to complete the calculation of e without using a temporary variable. Iterative function a.iterate at axa of sequence a has two parameters x and a. We will neglect the at a here for the moment, simply think that at a is a part of the function name, i.e., the function name is iterate at a. We'll talk about this at soon. As a loop function, a.iterate at axa will calculate x for each member of a. Tilde and hash can be used in expression X to represent the current member and sequence number of A in the loop, which is the same as other loop functions. The difference is that the symbol tilde is also provided in the iterative function, which is used to represent the X calculated in the previous cycle. When the loop starts, the initial value of tilde is the parameter A. After all members loop, return the sequence of tilde, which has the same length as A. The function A.iterate xa without at A is defined as the last member of A.iterate at AXA, that is, the intermediate process is no longer integrated into the sequence, only retain the last tilde. Let's go through a few examples. 1. The initial tilde is 0, the current member tilde will be added to tilde in each round of the loop, and finally we'll get the sum of all members, namely A.sum. 2. At A retains the results of each round of calculation, that is, the cumulative value from the beginning to the current member, which is equivalent to the loop function A.0.sum. 3. Inf is infinity, negative inf is negative infinity, which is the minimum number. In each cycle, if the current member tilde is larger than tilde is replaced by tilde, and the final result is A.maximum. 4. This is similar to the previous one, and we'll get A.mean. 5. After analysis, we can see that it will be calculated as A.count. It seems that the iterative function is the parent function of these aggregate functions, which can be defined by the iterative function. It is easy to define an operation of successive multiplication of sequence members with iterative function. Factorial operation is a special case. In fact, A.x can also be interpreted as or. Iterative function is indeed the parent function of other loop functions. Now we can calculate E in one line. The iterative function in the middle will also be calculated as a sequence of factorial values. Section 5. Positioning and selection. It is a common operation to extract a subsequence from a sequence, that is, to extract a subset from a set. We have learned to use the to-function and sequence of numbers to extract a subsequence according to the position of members. Sometimes we want to get members from the end of a sequence in the reverse order. Of course, we can use the length of the sequence to calculate the sequence number, but it's a bit troublesome. SPL provides the function A.mi that can use the reverse order. The function A.mi will get the i's member of A. If I is less than 0, it will get the negative i's member counting from the end, that is, A.mi equals A. If I is larger than 0, return I, otherwise, return I plus A.len plus 1. Similarly, when P is a sequence of length k with negative members, there is a function, A.mp equals sequence A.mp1 until A.mpk. We often use A.m-1 to get the last member of A. Pascal triangle can be simplified a little bit. We can also select members by a certain step size like this. Starting from the i's member, select 1 every k. A.step 2.1 will select the odd-numbered members, and A.step 2.2 will select the even-numbered members. Of course, it is more common to select members that meet a certain condition. A.select x returns a sequence of members in A that make x true, where x can use the symbols allowed in loop functions such as tilde and hash. The select function is called a selection function, and is also a loop function. The select function is very common. Let's give some examples. The constant sequence of column B is the result of the select function in column A, and A5 is further selected on the basis of A3. In fact, A.step can also be represented by select function, that is, the sequence number is used as a condition to achieve the result of selection. Using these functions, we calculate the prime numbers below 1000. A composite number below 1000 always has a prime factor of no more than the square root of 1000, that is, less than 32. We only need to use the integers below 32 to filter the sequence to 1000, and exclude all the multiples of these numbers by filling in the corresponding members as 0. The remaining members that are not 0 must be prime numbers. A1 generates the target sequence, B1 excludes 1 since 1 is not prime, that is, fill the member of the position with 0. Then A2 loops from 2 to 31. If the member at this position is already 0, it means that it is a composite number, leave it alone, skip to the next cycle. If it's a prime number, pick out the positions of all its multiples, that is, A1. Step A2, A2 times 2. Pay attention to start from A2 times 2 and skip A2 itself, because A2 is a prime number and needs to be kept. Then, the members in these positions may have 0, which indicates that they have been screened out in the previous round. To exclude them, use select tilde larger than 0 to keep those that are not 0. The members in these positions are multiples of A2, that is, composite numbers. Set the members in these positions to 0, and then enter the next round. At the end of the loop, select the remaining non-zero members, which are all prime numbers. By the way, B4 calculates all twin prime pairs on this basis, which are the prime numbers with difference of 2. Using the select function and a dot function that we've learned, and the result is a two-layer sequence. The selection function will get members out of the sequence. In the other way round, we will also care about whether a data is in the sequence and its position in the sequence. The function a.pose x will return the position of x in A. More strictly, it is to find an I such that AI equals x. If multiple AI are the same as x, it will return the first one. If not, it will return null. The latter case is more commonly used, that is, whether the return value of pose function is null is used to determine whether a data is in the sequence. Similarly, there is an a.pseg function. For a sequence A with increasing member value, that is, AI is less than AI plus 1, the function will return the segment where x belongs, that is, if AI is less than or equal to x less than AI plus 1, pseg will return I, if x is less than A1, it will return 0, if a.m-1 is less than x, a.len is returned. We take the increasing sequence as an example to explain the principle. Actually it also works for decreasing sequence, but these less than signs should be changed to greater than signs. In our daily work, we often need segmented statistics, such as age, sales amount, etc. We can use the pseg function in these cases, but we will give these examples after we have learned structured data. In theory, there may be duplicated values in the previous example of digital black hole, that is, A becomes B becomes C, and C becomes A again. In this case, it will lead to endless loop, but our current program can't discover this situation. Only because we have done our homework in advance, we know for sure that there is only one single black hole in the 4 digits, so the code is written like that, but it may not be the case for other digits. The pose function can be used to find this kind of loop, and the pseg function and insert function can also be used to improve the sorting. This program can find the digital black hole of any number of digits, A1 is the number of digits and B1 is the starting value. Here we use the various techniques we have learned before. C1 uses run to calculate a sequence 1, 10, 100, etc. C2 uses it to get the number of each digit. Sorting needs only one line now, and the current result is saved in B2. B3 loops for each digit. In C3, pseg is used to find out where the new digit should be inserted. In D3, insert function is used to insert it. At the end of the loop, B2 is the sequence sorted from small to large. B4 and D4 use C1 again to calculate the large number and small number. The at in B5 stands for itself. When the program starts to run, it will automatically clear all the cell values. The expression will continuously accumulate the calculated numbers and record them in a sequence. In B6, if it is found that the newly calculated number is already in the sequence, it means that the duplicated value appears and the program should be stopped. It should be noted that pose and pseg are not loop functions, and the symbols such as tilde hash cannot and need not be used in the X of their parameters. If they are used, they are considered to belong to the loop function of the upper layer. These functions may be nested in a loop function. These principles will be further explained at the end of this chapter. We care about the members that meet the conditions, but sometimes we also care about the positions of those members. For example, we want to find out in which months the sales amount has increased from a sequence of 12-month sales amount. Using the select function can only find the growing members, but not the positions of the growing members. The a.pSelectX function can help us by returning the sequence numbers of members that make X true. In terms of the symbols of a loop function, select will return a sequence of tilde and pSelect will return the corresponding hash. pSelect is called the positioning function. Let's try. We expect the result of column A to be the value of column B, but it is not. A2, A3, and A4 return 2, 3, and 1 respectively, which is only the first value in the sequence of column B. What's going on? It turns out that the pSelect function is defined as such that it only returns the first hash that satisfies the condition. So, what should we do if we want to return all the qualified hash like select? Just add @a after the function name. What is this? The writing method of @a is invented by SPL, which is called function option. In theory, pSelect and pSelect@a are two unrelated different functions, but these two functions are very similar. They are both for sequences, and the parameters are the same. Although the functions are not exactly the same, they are very similar. In this case, we are more willing to regard one of them as a variant of the other, and use similar names when naming, which will be more convenient for understanding and memorizing. But these two functions are still different and need to be distinguished. In SPL, we use the same name to name these two functions, and use the character after @ to distinguish them. It seems that a function has different modes. When there is no @a, pSelect only returns the first one, and when there is @a, pSelect will return all values. There are many functions with options in SPL, and there are often more than one options. For example, pSelect also has a @z option, which means to search from the end and in reverse direction. In the above example, a1.pSelect@z, %2 = 0, will return 6. Moreover, these options may be used in combination. a1.pSelect@az, %2 = 0, means to find all the hash that meet the condition from the end and in reverse direction, and the result will return 6, 5, 2. There is no order in the writing of options. pSelect@az and pSelect@za are the same. Correspondingly, the select function has a @1 option, which means that the first member satisfying the condition will be returned. The reason for this design is that it is more common for select to return all values, while it is more common for pSelect to return the first. SPL function options can greatly simplify the code. At present, there is no such syntax in other programming languages, and the function of some languages also has the concept of option, but it generally exists as an independent parameter. We will see later that in structured data processing, parameters are very complicated, and it is not convenient to pass option information as parameters. We use the max function to find the maximum value of the sequence members. Similarly, we may also care about the position of the maximum value. SPL also provides a .pmax function to return the position of the maximum value in sequence A. The maximum value of a sequence is unique, but there may be more than one member with the maximum value. Therefore, pmax is similar to pSelect. By default, it returns the position of the first maximum value. If the option @a is added, it will return all positions, and @z will search from the back to the front. The pmax function is not difficult to understand, so we don't give examples here. And, of course, there is also pmean function. We mention pmax here to deepen the understanding of positioning function. Pmax is also a positioning function. Positioning is a common operation, but there is no corresponding library function in many programming languages. SPL pays special attention to this kind of operation. Forget to mention that the pose function also has @a and @z options. It's easy to ignore that there is another selection function maxp that is related to max. A.maxp is defined as aa.pmax, which is the member that returns the maximum value. If you think about it, isn't it a.max? Why create a new function? It's still different. In a simple way, a.pmax has the @a option, which may return multiple values, so that a.maxp@a may also return a sequence, but a.max will not. However, even if a.maxp@a is a sequence, the members are all the same. It doesn't seem very interesting. The bigger difference is in the case of with parameters. A.maxx returns the maximum x, while a.maxpx returns the member that maximizes x. For example, see the difference? Max returns the maximum value itself, while max p returns the member that makes the maximum value appear. For just a sequence, they are the same, but with an expression, you can find their difference. In the structured data processing that will be covered later, this kind of calculation is very common. For example, we often care more about the product that leads to the highest sales amount than the highest sales amount itself. Max is not a selection function, it returns a value. Max p returns a member or sequence of members, and is a selection function. Like positioning function, selection function is also a big kind of operation. Of course, there is also mean p function. Section 6. Sorting related. In order to solve the problem of digital black hole, we have written several sort codes. Sorting is really a very common action, so SPL provides sorting function directly. A.sort will return a sequence that arranges the members of A from small to large. Of course, we often use sorting from large to small, just use the Z option. The sorting function returns a sequence composed of the original members of the sequence, which can be understood as a type of selection function. It also has a corresponding positioning function. A.pSort will return a number sequence P, so that AP is arranged from small to large. In other words, A.sort equals AA.pSort. Please try to understand the meaning of this equation. Try it. As a rule, the result of column A is the constant of column B. With the sorting function, the digital black hole can be simpler, without using pseg and insert. Sorting function also supports the case of expression A.sort x, but it is not equal to A.x.sort. It is defined by pSort, that is, A.sort x equals AA.pSort x, and A.pSort x can be defined by A.x.pSort. This is the same as the case of max p, which is the common feature of selection function and positioning function. The same is true for select function, that is, A.select x equals AA.pSelect at AX, not A.x.select. However, SPL does not provide a function that is consistent with A.maxx style and can directly return A.x.sort, so this requirement can only be calculated with this expression. This is caused by historical habits. In the early programming languages, sort function was designed in this way. Sorting is generally used to get a neat order, but it can also be used to disrupt the order of a sequence. The rand function in B1 will return a random floating point number between 0 and 1 in each calculation. The random number is disordered, and the order of sorting is disordered. As a result, A1, which was originally very neat, is arranged in a disordered way. If we develop a poker game, this principle can be used to shuffle cards. The method of disrupting the order can also be used for sampling. For example, we want to select 100 numbers randomly from the range of 1 to 1000, which cannot be repeated. It's not easy to generate them randomly, and it's troublesome to regenerate them if there is repetition. It is very simple using the above sorting method, just getting the top 100 after disrupting the order. We'll explain a little more about the rand function. It is very convenient to use random numbers to generate test data. However, when we find an error in the test, we hope to run the same set of test data again to find out where the error is. But random numbers are random, and another batch is generated after the second calculation. In fact, there are no real random numbers in the computer, but a series of calculations are carried out to get new numbers from the numbers generated last time. When the calculation rules meet some mathematical principles, it is difficult to see the pattern, and it can also ensure that the calculated numbers can be evenly distributed within the specified range. These random numbers are called pseudo-random numbers. As long as the first number is determined, the sequence of the numbers calculated is determined. Using this principle, we can create the same random numbers. Rand@ss function sets the parameter s to the first random number, called the seed. Running this code shows that B1 and B3 are the same. So, if the seeds used at the beginning of each program execution are same, then won't the generated random number sequences all be the same? No, when the program starts, it will automatically execute a statement like rand@s_long now returns the current time, that is, the start time of program execution is used as the seed. This is operated by human and has enough randomness which can ensure that different random number sequences will be obtained before each program execution. Looking back, psort is not only used to define sort, but also useful. Look at this code. The rand n in B1 means to return a random integer below n, regarding A1 as the student numbers of a group of students. Actually, we should use names, but wait until we learn about strings. We just use integers as student numbers for now. B1 can be understood as the scores of these students, which correspond to the members of A1 one by one. Now we want to get the result sequence of these student numbers sorted by their corresponding scores. It's obviously useless to sort A1, while sorting B1 can sort out the score itself, but it can't get the sorting of student numbers. Using psort can solve this problem. Now B2 is the student number sequence that we want to sort by score. When the number of members is large, the sorting of the whole sequence is slow and often meaningless. For example, there are the sales of tens of thousands of stores. We usually only care about the top few and the corresponding sales amounts, and we are not interested in the situation after hundreds or thousands. And to get the top few, there is no need to sort the whole sequence. SPL provides the top function to get only the first few. Similarly, there is the ptop function, but the syntax rules are a little different from the sort function. Because the top function has three cases similar to the max function, max that returns the value, positioning function p max and selection function max p. The positioning function a.ptop_n returns the positions of the smallest n members. When there is a parameter, a.ptop_nx is defined as a.x.ptop_n. It is similar to p max, which is not difficult to understand. A.top_n can be defined as a.ptop_n. When there is no x parameter, it is both a value and a member. It can be analogized to max or max p without ambiguity. However, with the x parameter, a.top_nx is defined as a.x.top_n, which is equivalent to max, is for the value. The selection function is represented by a.top_n:x, and it corresponds to max p. Note that a semicolon is used to separate parameters instead of a comma. Maybe because the word top p really does not look good, it is not used. Here n can't be omitted. In SPL, there are a lot of cases where semicolons are used to distinguish parameters. We will talk about it later, so that we can distinguish them. Generally speaking, the function style designed in SPL is relatively consistent, and it is easy to make an analogy between different operations. Section 7. Lambda syntax. Looking back at the two functions a.posex and a.selectx, we say that the former is not a loop function, and the symbols ~# can't be used in the parameter x, while the latter is a loop function, and the symbols ~# can be used in the parameter. In fact, in the calculation process of these two functions, both of them will traverse a, that is, they will process the members of a one by one. What is the difference between the parameters of these two functions? Before the introduction of loop function, all functions fx has one characteristic. If its parameter x is a calculation expression, it will be calculated before calculating this function f. For example, max 3 plus 5 2 plus 1, when the computer calculates max function, the parameters obtained are already 8 and 3. It's the same case even if there may be variables in the parameters. The calculation expression of max x plus 5y plus 3 cannot be calculated when x and y are not assigned, and after x and y are assigned, x plus 5 and y plus 3 will be calculated first and then transferred to max function for calculation. That's okay. That's what we learned about functions in math class. So is the parameter of a.posex. However, a.selectx is different. This x may not be calculated before calculating the select function. It can be calculated only in the process of calculating the select function. For example, a.select %2 == 0, we can't calculate %2 == 0 before calculating the select function. There is an unknown tilde, which can only be determined in the process of looping a, and then we can calculate this expression. For the function of sequence, its parameter is an expression to be calculated, which can only be calculated in the process of looping the sequence. The function with this characteristic is called loop function. Therefore, a.posex and a.psegx are not loop functions, while a.x, a.runx, a.selectx and a.maxx are loop functions. For non-loop functions, even if the parameters are written as expressions, they will be calculated as specific values when they are passed in. For a loop function, the parameter to be passed into the function is an expression which contains some unknown variables such as ~hash. In fact, this expression can be regarded as a function with these unknown variables as parameters. In other words, the parameter of a loop function is essentially another function, not a simple value. This is the essential difference between a loop function and non-loop function. It takes function as parameter. The earliest programming languages did not support functions as parameters, and people were still inexperienced at that time. They simply used the experience of functions in mathematics. Later, in order to make code reuse more convenient, people introduced the concept of function pointer, and passed the function as a parameter to another function, so that the former can be called by the latter. However, it is still necessary to clearly define the called function with a piece of code. The code is complex and difficult to understand. For example, a.select %2 == 0 in our example, the traditional syntax is divided into two steps. First, define a function fx as x%2 == 0, and then use a.select f to calculate. In the loop calculation of the select function, the current member of a is passed into the function f as a parameter. After calculation, the return value is obtained, and it is decided whether to add this member to the return value of select. In fact, the calculation logic of many functions that need to be used as parameters is not complex. It can be described clearly by a simple expression. For example, this x%2 == 0 is very simple. It's too troublesome to define an f function for such a matter. Therefore, people further invented the programming syntax to define a function directly with an expression. Instead of defining the f function in advance, it can be directly written into the parameter of the select function. For example, it can be written like this. This method of temporarily defining functions in parameters is called lambda syntax in the industry. With lambda syntax, code writing is much easier. Now many programming languages have begun to support this syntax. There are still problems. The function to be passed in must be a function with parameters which are used to refer to some variables like the members of a here. Such variables are generated in the calculation process of the host function, that is the select in this example. Otherwise, if there are no parameters, it should have been calculated before calling the host function. Therefore, in the above fx:x%2 == 0 in braces syntax, there must be a way to specify the parameter. Use x in fx to tell the computer that x in x%2 == 0 is the parameter of the function as the parameter, and is waiting for the host function to pass the value in. If we only write x%2 == 0, the computer doesn't know what x is, or is it a variable somewhere else? It's still a bit cumbersome and confusing to understand, but this is the status quo of most programming languages that support lambda syntax. It's not over yet. The sequence number of A's members, that is hash, may also be used in the host function of select. It is not enough for the function f to have only one parameter, because the select function needs to accept all kinds of functions as parameters, and the parameters of these functions must be unified, otherwise the select function cannot call them. Therefore, this function must have at least two parameters, and the syntax must be written like this. In this example, we don't use the y parameter prepared for the sequence number, that is hash, but we have to write it in the definition. However, we know that select may also use -1 and so on. How much more will be passed in? These parameters need to be defined as parameters of f in advance. It's too troublesome. Just pass in the whole A and then the current sequence number. Anyway, it can be calculated. Finally, it may be written like this. The parameter x represents the sequence to be calculated by the host function, and the parameter y represents the sequence number of the member being calculated by the host function. The rest is written in this definition. But that's inconvenient again. In fact, most of the programming languages that support lambda syntax do not come to this stage, and they only support to the level of fx:x%2 == 0 in braces. In other words, there is no way to refer to sequence numbers and make adjacent references in expressions. So, how can we make the code simple and descriptive? That's what SPL does now. SPL simplifies this matter by using the symbols of tilde and hash and square brackets to represent the parameters of the function as a parameter. Therefore, it is okay to write tilde %2 == 0 instead of writing fx to specify the parameter name. In this way, writing and understanding are simple, and because of these rich symbols, the description ability is also strengthened.